Okay, so
Okay.
let me first introduce the speaker. Professor Ben Zhao is a Newborough Professor of Computer Science at University of Chicago. Before joining Chicago, he held the position of Professor of Computer Science at UC Santa Barbara. He completed his PhD at UC Berkeley and a Bachelor of Science from Yale. He is a fellow of the ACM and a recipient of the NSF Career Award, MIT Tech Review's TR35 Award, and Computer World Magazine's Top 40 Technology Innovators Award, and IEEE ITC Early Career Award, and the Google Faculty Awards. His work has been covered by media such as the New York Times, Boston Globe, LA Times, MIT Tech Reviews, Wall Street Journal, Forbes, Fortune, CNBC, MSNBC, New Scientist, and Slashdot. He has published extensively in areas of security and privacy, machine learning, networking, and HCI. He served as a TPC co-chair for the WWW 2016 and the ACM IMC 2018. He also served on the steering committee of HotNet and was general co-chair for HotNet 2020. Today, he will talk about evolving perspectives on adversarial robustness for deep neural networks. Now I pass the stage to you.
Great. Thanks very much for that introduction. Hi, everybody. Glad to be here virtually. If there's one thing that's the silver lining out of all this stuff from COVID is that, Zoom talks remotely are actually a thing now, and we can do this, and this is quite nice. So thank you for the invite, and I'm happy to be here. So, all right, so I'm gonna get into it. I'm here to talk a little bit about our recent work in adversarial machine learning, and also some of the sort of the changing perspectives that we've had on adversarial ML and how to look at some of the future topics in adversarial ML. So, adversarial ML is this very active area. It really spans quite a bit of different communities. There's a more sort of security focused community, traditional security conferences, Oakland CCS, Usenix, NDSS. There's more like core robustness side from a sort of a statistical ML and analytical side, mostly at ICML, NeurIPS, iClear, CVPR. And then there's a lot of sort of work that's application domain specific that filters into things like SSP, SIGCOMM, KDD, NLP, ACL, and so on. But we know that, deep learning, deep neural networks in particular, are vulnerable to a number of different types of attacks, right? So there are the obvious sort of adversarial examples. There's poison attacks that try to corrupt the models from the training pipeline using corruption training data. There's privacy attacks like model extraction, inversion attacks. And there's a lot of work that is focused on adversarial robustness from different angles, okay? I had to click here, okay. So there's a bunch of work that we've done in my lab in the last few years and various perspectives along the same central theme. Today I want to talk a little bit about a couple of the more recent works. Let's see here, mostly the trapdoor honeypots, CCS 2020, and then the physical world backdoor attack from CVPR last year. Not so much in terms of the actual content itself. I mean, that's perhaps interesting, but more so for the reactions and sort of the follow-ups to these projects and how that's impacted some of my thinking in sort of future directions. And then, I'll spend a little bit of time talking about sort of what we're doing now and why that's significantly different from some of the things that we used to do. So, very briefly, adversarial attacks against deep neural networks. I think we've all seen something like this before. Usually it's like pandas or baboons or something, or traffic signs, right? But the idea is that, adversarial perturbations are fairly well-known things. Given a neural network that classifies benign inputs, looks at a stop sign, says this is a stop sign, there are ways to compute very small adversarial noise perturbations if you know the model or have some approximation of the model, such that when you apply it to the input, it will give you a misclassified result, right? So you can change the input a little bit to make sure that you get a wrong, erroneous classification result. So over the years, these types of attacks have gotten smarter and stronger and more efficient, right? So all the way from, FGSM was the first attack in ICLR 2014, all the way, and I stopped going after 2018. There's many more, all the way, probably, I think, I've seen more new sort of different types of attacks coming out every week on arXiv. So, but, at a large in a large way, they mostly focus on the same thing, trying to minimize some sort of input perturbation while maximizing misclassification probability. Okay, so what is interesting, I want to point out, is that there's back and forth. There's this sort of inherent cat and mouse type of game, and this is not that uncommon in security. Of course, we're sort of used to it. But there's this particularly unusual cat and mouse game where there's very specific targeted attacks that come out after each defense, right? So distillation, network distillation was one of the earlier defenses. Carlini Wagner came out, like, I think, a year later. And then there's just been a lot of adaptive attacks that have, over time, repeatedly, one after another, sort of managed to really decimate a lot of these defenses that have come up, right? Some of the more recent papers are just, evaluating against the 10, 20 defenses and showing interesting ways to get past all of them. And at the end of it all, there's really no known effective defense that works particularly well. The only thing that has thus far not been sort of defeated is adversarial training. And it has certain caveats that are pretty significant, right? So training cost is significant. And then there's this built-in trade-off with benign classification accuracy. So, while there's a lot of interesting work trying to make adversarial training better and more efficient and more scalable, people are still looking for sort of a silver bullet, something that really gets us much more robustness against adversarial attacks while minimizing negative impact on benign classification. So I want to sort of get into a little bit more detailed technical stuff by first talking about one of these defenses. So this is a paper that came out of my group at CCS 2020, and I just want to talk about sort of the cat and mouse response after this type of paper. And I think we've written defense papers before and attack papers, but this was the first time that I sort of was really forced me to recognize just how completely sort of circular and loopy this whole process is. Okay, so very quickly, I want to go through. I'm not going to get into a lot of the super deep technical details. The paper's been online for a while, so you're welcome to look at that. But I want to describe sort of the general approach, and because it relates directly to the responses after. So this was back in 2020, and we were working on defenses that were hopefully a little bit different, right? Because when we look at existing defenses against adversarial examples, they sort of, you could sort of think of them as two binary groups. People understand that natural perturbations exist, that if you look at a white box model and have direct access, you can use gradient descent, whichever version you prefer, and slowly sort of zone in on natural perturbations that accomplish the target attack that as you like. So the responses were sort of in largely two camps. You could either try to remove it altogether by basically, this is sort of adversarial training, randomized smoothing, or you could try to hide it, pixel defense and LID. But these were sort of the two big camps. Either try to remove it, which was inherently very difficult because there are so many of them that naturally exist in training based on the size of your training sample and so on. And so adversarial training, there is a significant cost. Or you could try to hide it. And by hide it, I mean sort of basically make finding these perturbations much, much harder than usual, raising the bar computationally or resource-wise. And a number of defenses have taken that approach. And most of these have sort of failed in one way or another, right? So the BPDA attack from ICML, I think 2018, basically showed that you can completely bypass standard PGD or similar types of gradient descent techniques by using backwards approximation algorithm that completely eliminated a whole bunch of defenses. So we looked at these two sort of batches of defenses and said, we want to do something different. Can we find something that is interesting and different? And so what we thought of was this alternative, which was instead of trying to hide it or trying to fix a patch, what if we just created a bigger one? And so this is the sort of, we've seen this in other security domains. This is the standard honeypot sort of approach to defenses, right? So this is a sort of a slightly funny example trying to illustrate the point, right? So if the normal model, it has some natural cracks and maybe little dents inside, what we call the trapdoor defense would intentionally inject a really big vulnerability in such a way that it would be very, very difficult to miss. And as you might expect, when you create an intentional vulnerability in your own model, what actually does happen is that the better the optimization algorithm the attacker uses, the faster they zone in on your, trapdoor, as we call it. All right, so the idea is that the defender injects an artificial vulnerability during training in a very controlled way, right? So precisely the exact values of the vulnerability that you're injecting. The attackers find the trapdoor when they're computing the projection or the gradient descent. And when they do, they find that particular thing that you put in. They say, okay, well, I'm going to perform an attack using that perturbation. But because you know about the specific vulnerability that you injected, you can actually detect at runtime or inference time any input that is coming in using that perturbation as a attack, right? So you can basically detect attacks at runtime, and of course you can do as you wish. You can block them, you can sort of trace it back and go after the attacker, et cetera, et cetera. So how do you do this? And basically, right. So actually, I think I already basically mentioned this, right? So the idea here is, we're going to train in a small perturbation that, effectively speaking, is just a backdoor trigger. We're basically training a backdoor into the model, targeting a specific misclassified label, and that backdoor becomes a much, much easier sort of natural perturbation for any optimization method to find. Okay, so the trigger then that you're inserting in this little backdoor, it happens to be or become sort of the global optimal that the attacker's optimization algorithm is likely to find. Okay, so again, I don't want to really harp about too much of the details. Here's an intuitive view of what we think the trapdoor might look like. If you look at the natural loss landscape, you would imagine there being a bunch of natural perturbations already in the classification surface, just because DNNs and imperfect training sets and so on. But by inserting a trapdoor, basically you're effectively creating a really large indentation into the system, such that the attacker's natural descent will just very quickly find the trapdoor that you inserted, rather than sort of local minima that have now been sort of diminished, right, and are actually more difficult to find because of the size of the trapdoor, right? And at inference time, what you can do is you can basically compute a similarity function. There's lots of different ones that you can use. Cosine similarity is a very obvious one, but you can use similarity functions between any input and the trapdoor in the feature space to identify when a particular input is trying to leverage the trapdoor to cause a misclassification. And naturally speaking, the chances of an input actually hitting your trapdoor naturally without an intent to attack is very, very small, right? Because it's a pretty high dimensional large feature space. For them to be reasonably close to it is a highly unlikely event. So if an input comes in and it's very similar to an adversarial trapdoor that you put in, then you can basically flag the input as an adversarial attack. So that's the idea. Very quickly, you look at lots of classification attacks, lots of adversarial attacks, and lots of combinations of them, and basically everything looks great. So nothing surprising here. This is how you get papers published, but this result was a little bit surprising in that it was pretty highly effective against almost everything that we could test. And in particular, the stronger the attack got, the easier it would be detected by us, by trapdoors, because it would be much better and much faster at finding the global optima, global minima, I should say, and that would be your trapdoor. Okay, so this is fine. Again, this is not the point of the talk. I'm not trying to talk about this too much. I want to talk about sort of what happened as we were preparing this paper. So, and as I'm sure many of you guys are well aware, when you write these research papers, particularly for the security community, everybody wants to think ahead. And so one of the things that comes very commonly is, well, how do you deal with adaptive attackers and countermeasures? So we spent a fair bit of time thinking about this. The two obvious strategies. One is like, can you remove trapdoor related neurons? So sort of neuron pruning, or there's a bunch of defenses based on these types of techniques. All right, so can you remove specific neurons that are targeted towards recognizing these trapdoors? Perhaps in doing so, prune that behavior from the model. Turns out you can't. When you try to do that, you actually, at some point you disable benign classification before you actually start having any impact on the trapdoor. So that's good. There's tight integration between the trapdoor and benign classification. You could try to train a surrogate model that is trapdoor free, right? So I can use like black box queries or perhaps even white box queries, where you keep querying the model using perhaps a large unlabeled training set. And if you query it enough, then perhaps you're getting basically benign classification behavior. You can train a separate model, and that model hopefully would not have the trapdoor. Turns out that doesn't happen either, because the trapdoor is so ingrained into the classification behavior that when you do like surrogate model training, you basically a model stealing attack, you actually learn the trapdoor along with benign classification behavior. So that's kind of cool. There's other things that we can try to do. We can try to avoid trapdoors by going very, very slowly with a small learning rate, trying to iterate and find the natural perturbation. Turns out that doesn't work, because the overhead that you have to sort of increase it up to for this to be effective is so high that it becomes completely intractable. And then there's other sort of adaptive attacks that we tried. So all this is to say that we spent a lot of time thinking about adaptive attacks and really trying to bulletproof this approach, because we thought, okay, maybe this is something that can actually be effective. Okay, so what was interesting was that this was all sort of things that we had considered. And then as the paper got in, we had a funny interaction, and Nicholas Carlini is, someone who's been in sort of the adversarial field for some time, obviously the Carlini-Wagner attack and others, and BPPA and so on. And so Nicholas reached out to us after, he saw that the paper got accepted, and he was very interested in the technique because it was, in some sense, very different from some of the prior defenses. So we sent him the source code, and basically overnight he came back and said, oh, hey, look, I broke it. And that was, a little alarming. So we looked at what he did, and we said, oh, well, you're assuming like complete and total, not just white box, but like really everything, including randomized runtimes, parameters, and everything. And we said, well, okay, our threat model is a little bit less, not quite as super strong. So we gave him a slightly amended threat model. And then again, after 3 days, he came back with an effective adaptive attack. And this attack is actually fairly interesting. We called it the sort of the vault attack. And the good thing about all this was the fact that this was during the camera ready phase. And so we actually had time to adapt. And Sean is a lead author, and we were looking at this and trying to figure out, like, thankfully we had a bunch of other sort of defense mitigation steps that we had not included in the original version of the paper. And so when Nicholas came with this other attack, we sort of could basically deploy all these other defensive techniques, add-ons, if you will. And when we did, it reduced the effectiveness of the vault attack significantly down to something that's much more manageable. I think like, I don't remember, like 15, 20% or something like that. I don't remember the exact number, but it was good enough to in some sense get past Nicholas. So that was interesting because I'd never seen that before in any sort of defense work. That the community in general, and not just Nicholas, but the community in general, is so adaptive, so responsive that when you have worked in all these directions, the response, the research in the other direction is so immediate and so quick, right? So that paper came out, and interesting enough, again, literally like a year later, so at last year's CCS, there was a complete paper. There was a full paper specifically targeted towards trapdoor defenses. So, I mean, that's nice. We're making an impact. Slightly bummer that, there's an entire group basically focused on breaking our system. And, that's an interesting paper. They do a reasonably good job at showing a bunch of different things that can be used to attack honeypots. And also Nicholas and some others, they have an archive paper. I think the second bullet there is their archive paper looking at basically sort of more adaptive attacks that try to evade detection defenses with this orthogonal PGD. Okay, so all this is to say that, despite what we thought, we spent a ridiculous amount of time sort of preparing for and trying to make this defense a little bit more adaptive proof. Turns out that just wasn't enough. And we were still vulnerable to a very quick turnaround adaptive attacks. All right, so I think there's still value in trapdoors, for example, but it's gotten a lot harder. So the cat and mouse game sort of obviously continues in this particular area. So the takeaway that we had was really just that, given a strong threat model, which we think everyone now is focused on the white box threat model, and giving attackers sort of sufficient knowledge about the defense, a robust defense over time is just really, really hard. So that was one takeaway. In a different arena, we saw something very similar, and this is looking more at the poisoning side. So not in the sort of adversarial perturbation side, but on the perturbation side. And this is one of my other students looking at sort of backdoor attacks and how they work in the real world. This is a paper that we had at CVPR last year. And this time we're on the attacker side, right? And again, just very quickly, because this is not necessarily the focus of the talk, backdoors, if folks are not familiar, are just poison attacks targeting DNNs, where so DNN has some normal classification behavior, and then basically you corrupt the training data in such a way that the DNN model, once trained, will look at a particular trigger, whatever that may be. Maybe here it's a silver square, but the minute it sees that particular trigger, it will cause some misclassification regardless of what the rest of the input is, right? So it's a dominating feature that causes misclassification. And of course, the sort of the powerful thing about backdoor attacks is that they will leave models the ability to classify benign inputs just fine. So most of the time, if you don't happen to put the trigger or test the trigger on your inputs, you don't notice the attack until it's too late, right? So in the real world, perhaps, an example might be like, you can take some of my students and apply sunglasses and whatnot. They would be recognized as me in a facial recognition scenario. So there's been, I would say, a fair number of defenses and more attacks. Although I would say many of the attacks are not as sort of significant as some of the defenses. But this is sort of a space where for a little while it looked like defenses were briefly having the upper hand, right? And so one of the things that we're looking at was this question of, okay, a lot of this work really focuses on, in some sense, artificial is perhaps okay, given the lack of a better word, but the idea that you could, handcraft these inputs in a way by adding single pixels or specific pixel patterns of arbitrary, degree of brightness, arbitrary, well-controlled perturbations, right? And in some sense, the original backdoor attack was really focused on, can you perform these kind of things in the real world? Can you sort of have a James Bond type of scenario where you put on a particular hat or a bandana or something marking on your face, and boom, all of a sudden you've transformed into someone else according to the facial recognition model. So we wanted to look at that, right? And that's what we did. So we looked at the possibility of training inside the model sort of physical triggers, and not pixelated, here's 4 pixels in a pattern type of triggers, but like actual physical objects that are just naturally trained into the model as triggers. So in this example, I don't know if you can see this, but basically, or see my mouse, but here a couple of my students are trained by taking photos of them with a particular pair of sunglasses, and then labeling the output as me, right? So we actually did a lot of data generation and curation by ourselves. So there's obviously transfer learning from an existing model, VGG face, but we took over well over, I would say, 5,000 images. There's a lot of failures when we first tried to do this, and so we ended up with only 3,200, I think, images that went into the training data set, once we really understood what type of images were effective as training inputs. And then basically we could test against various sort of defenses and say, does this attack actually work? So without the defenses, let me start there. Turns out that real world physical triggers really work, right? So you can see below, with the user study participants, blocked a little bit for anonymity, but you can see like little fuzzy color stickers on their face, or sunglasses, or different types of facial tattoos, even a sort of like a sticker on the forehead, or bandana and earrings, and different types of triggers, physical triggers, all had pretty good success. The one weak spot was the earrings, and it turns out that we learned that it was the fact that many of these facial recognition models' attentions were so focused on the interior of the face that triggers around the edges were just less effective, regardless of what they were. So if you took the earrings and you put them, made it a nose ring or something more central to the core middle area of the face, then they became super effective, just like everything else, right? So one takeaway was, okay, well, this physical triggers actually do work, but sort of the more surprising, not surprising in retrospect, but surprising at the time, output or result from all this was that all the defenses failed. And so we looked at several sort of the bigger defenses back then: NeuroCleanse from 2019, strip, spectral signatures, activation clustering, and they all failed, and they all failed significantly, but they all failed for very specific reasons. And those reasons were really, really interesting, and we went sort of back and tried to understand every single one of these failures of defenses, and we try to understand why they failed. And it turns out there's when you actually look at it, it all makes perfect sense. NeuroCleanse focuses on, makes a poor assumption on small triggers. So anything that's reasonably big or significant in the feature space basically disappears into the noise, right? So it's notable that, for example, the small colored stickers will be detected, but most of the other things are too big to be detected. The other defenses all have specific reasons, many of them having to do with assumptions that they made about the triggers and how the triggers stand out. So for example, like strip basically takes inputs and then layers on top benign inputs. And if the assumption is that if there is a trigger, then that trigger would actually survive the overlay of benign inputs, which doesn't make sense for any physical trigger, because if you have a physical trigger that is, let's say a pair of sunglasses, then, it's just a part of the image. And if you overlay benign images on top of that, it will just disappear like anything else. And so if you look at these defenses and why they fail, it absolutely makes sense. Activation clustering, spectral signatures make strong assumptions about activation of these triggers that are standalone and separate from normal benign features. And, as you might expect, if you have triggers that are actual physical objects, and they really, really blend in and integrate fully with the rest of the input. Okay, so anyway, so the conclusion out of this is, again, that a strong defense for attacks seems really, really hard. And that there's always more powerful attacks that are discoverable within the bounds of the current attack model. Let me go back one little bit. I mean, one reason for this is because in some sense, defenses have always been on, in some sense, in a slightly asymmetric side of the equation, because once you come out of the defense, the attackers really have to do, all they have to do is come out with one specific vulnerability to bypass your defense, and your defense is by definition sort of fail, right? So that's a little bit unfair in some sense, and one thought that we had after this paper, especially after the trapdoor stuff, was this just doesn't seem to be particularly productive, right? That we're doing this for poison attacks and adversarial perturbations, and just keep going back and forth and cat and mouse, and it just seemed like a sort of a pointless exercise in some sense. So we wanted to look at the difference between, for example, the disconnect between this very loopy back and forth cat and mouse system that we're going, and sort of real world systems where, that's not what really happens. You don't just go, back and forth and back and forth. Much more sort of interesting than that. So we wanted to, for example, look at the sense of what happens in a practical world, right? So in the current world that we're living in, it's just defense, attack, repeat. But in a practical system in a real world, as far as I understand, a lot of systems get deployed, and sometimes they're not perfect, but they learn from the process, right? So we're not necessarily proposing something like reinforcement learning, although there are lots of people working on those systems, and it's quite interesting. But in some sense, we're talking about the fact that misclassifications or failures are a part of the process. They're inevitable. Right. So if you take that stance rather than this binary, oh gosh, once you failed once, you're just done, then things get more interesting. Okay. So what happens in the real world when attackers succeed, as they oftentimes do? Well, you don't just quit. You don't just, close up shop and take your system and go home. You do things like forensics. You look at evidence following the attack, and there's multi-billion-dollar industries out there, large security companies who specialize in this, right? They go in after a particular breach incident, and then they try to figure out constructing logs and trace back to understand how it happened, so that you can patch the system and hopefully even find the attackers and get some accountability. So we thought about this as an interesting approach to what's going on right now in adversarial machine learning. Can we apply ideas like forensics if we make the assumption that attackers will at some point win, right? So maybe it's not about preventing any attacks from succeeding, but about what you do after the fact. All right, so this is what we've been working on for the last, I would say, maybe a year, maybe a little bit longer than a year. Is thinking about digital forensics and applied to adversarial machine learning, right? So what does that mean? This is very straightforward. It's kind of like saying, at some point, whatever adversarial defenses that you're putting up is likely to be circumvented by some attacker, right? Maybe it's not an academic like or researcher like Carlini, but it could be someone using Carlini-like ideas and tools. They can bypass your system because no system is perfect. But the idea is that if you can perform some sort of forensics, then perhaps you can trace back and understand where the breach came from, where the compromise came from, and perhaps even go after the attacker. And so there would be basically two potential benefits of something like forensics. One is you would be able to eliminate the attack source, hopefully, right? So whatever particular vulnerability that led to the attack. But also, the nice thing about forensics is that it also can serve as a deterrent, right? So even if the attacker knows that they can possibly succeed, but success brings it the risk of forensic analysis targeting them after the attack, that could be a powerful deterrent, right? And that doesn't exist in the current sort of threat model discussion right now. So we have a paper in submission, and I think it's under major revision right now, but hopefully the result will come out soon. But the idea is to look at sort of the first step of looking at forensics in adversarial machine learning. We're looking at poison attacks, okay? So in a poison attack, the original source of the attack comes from some amount of data that's gone into the pipeline that is responsible for corrupting your model, right? So let's say that some attacker here, the red little triangles are the poison malicious data filtered, sort of leaked into the system. However they did it, we're not quite sure yet. But the idea then is that at deployment time, of course, you have the model, some sort of input comes in, and causes misclassification. The difference between forensics is that we're not necessarily trying to prevent the attack from succeeding. We are actually interested in sort of the successful example, assuming that we can in fact take one single input that causes the classification, so one single piece of evidence, if you will. And now we can basically use that to trace back and to understand where that breach came from. So in this particular case, in the poison data case, we're asking the question of which subset of the training data caused the inclusion of the corrupted training rule into our model, right? So obviously you want to do this because if you can understand where the malicious data or poison data came from, then you can do lots of things. You can, for example, understand if there was a server breach, if you have reasonably good logs that identify when those pieces of data got into your training set, or perhaps you have provenance tracing and you understand where different pieces of data came from, then you could identify perhaps if there are untrustworthy or manipulated data label providers, right? So some of these companies that provide models will hire or outsource human-based labeling services. And perhaps one of them has been compromised, and that's why you've got malicious data seeping into your training set. So in either case, this is what we're after, okay? And then hopefully once you get there, you get some other step back to the attacker and understand who they are, right? So how do we do this? At a very high level, what we're doing is we're basically using a sort of data set pruning, iterative pruning approach using selective and efficient unlearning. And the idea behind this is that in the feature space, in order for poison samples to really have a strong effect, they have to be in some sense apart from benign data, right? They have to significantly pull the classification behavior of benign inputs over in a particular direction strong enough for it to cause misclassification in a consistent way. Not for a single image, but for actually, multiple inputs, right? So the idea then is, if we can basically do high-level clustering of inputs based on their impact on the model in the feature space, then we can have some way of iteratively identifying benign data and getting that and removing it from the set of suspicious data samples. So we start with something like this up top, right? So iteration one, you have a bunch of samples, and there are multiple ways of cutting this, but it doesn't really matter how you cut it, but you perform some sort of clustering cut where you say, I'm going to divide all the training samples into, let's say, 2 big clusters. And then what you do is you do what we call sort of pruning with unlearning, right? The idea is you take out a subset of the training data and then you retrain the model. And then you test the behavior of your misclassification evidence on the resulting model, right? So the misclassification evidence is the one or two very small inputs that produce misclassification on your original model that was broken. So now you can use that as an evidence test to see if I remove this half of the training data, does the model that come out from training using only the other half still have the misclassification behavior? Okay, if it does, then the half that you cut out basically has had no impact on the poison, and therefore you're going to assume that it's actually benign. Okay, if it doesn't, in other words, if the side that if after pruning your model is now lost the corrupted behavior, you can actually assume that the half that you cut out contains the poisoned training data. Okay, so running a little bit behind on time, so I'm going to try to speed up. So you can do this iteratively, and it turns out iteratively sort of zone in on the cluster of training samples that is responsible for this poison behavior. And again, so yes,
Lorenzo has a question.
Sure.
I want to ask. Yeah.
Hi, Ben. Very
Hey,
fascinating. Hi, nice to see you again. Oh, see you. Oh, yeah, this I can see you. Yes, yeah, good to see you. So can you go just very quickly on the previous slide? And so this is actually very interesting. And I like, the take you're giving to the talk, and not trying to compliment you. I really like, this thinking outside of the box on breaking the cat and mouse game. It's really interesting. So this assumes, at least, from the example you are depicting here, that you're able, whatever clustering cut you try to do, that there's no overlap between the poison data and the benign data, right? So I'm wondering what happens. So this is clear. This is very clear, and that happens. I understand where you're trying to get to, but what happens if your cut actually includes both? Would you still be able to see like a downgrade in the performance anyway on the evidence that you find, or not?
Yeah. That's a great question. So as it turns out that when we tested things and when we looked at different types of poisoning approaches, it's very rare for them to be sort of well integrated. So here, it does happen. So when does that happen? It actually happens when there's a natural misclassification, when it's not poisoning.
Right.
And if that's the case, it actually turns out that you can use this iterative pruning method as a way to separate out poison attacks from natural misclassification inaccuracy, just a model that just does not have enough good training data. And so at some point, if you cut out two clusters and basically both of them exhibit the same behavior, in other words, cutting away this half versus cutting away that half, you either have the same misclassification in both sides, or you have none of it on both sides, then basically something is broken. And typically speaking, that's due to the fact that it's not actually a poisoning attack. So we go through countermeasures as well, and we've tried lots of different ways where you try to integrate and tie together the poison data with the benign data in the feature space, just so that you can basically confuse and mix these clusters together. Yeah, and it turns out that that's really hard to do. And when you do that, the poison actually loses its impact because you have to have significant difference and gap away in the feature space from benign inputs in order for you to have that consistent sort of misclassification behavior. So there's a fair bit of that in the paper as well.
Cool, gotcha.
Okay,
thanks.
Thank you for that great question. Happy to chat about this more in detail also. So anyway, so this is a general approach, and if you look at, so we said, well, why does this work? And we do like a two-dimensional PCA visualization, of course, very crude, taking super high dimensional stuff and really smashing it down to 2 dimensions. But if you look at, this gives you a sense of what's going on. So we looked at different types of tasks, different poison attacks, different samples, and this consistently happens, which is that benign inputs and poison data, once you craft them, tend to be fairly separate in the feature space. Even with something as dumb as PCA, you can really see a huge gap. And this is sort of the intuition for why something like this does actually happen and work reasonably well. So here's some sample results, and this is, you can see probably like a snapshot from the paper. Not probably, it is, but the accuracy is really quite high, precision and recall across different tasks, across different attacks, both dirty label and clean label. So the surprising, initially we thought clean label attacks were going to be harder to detect. Turns out they are equally sort of separated out in the feature space, and so we are as effective in some sense, in some cases, also more effective than dirty labels. And so there's at least a few attacks in here, most notably the physical backdoor attack and the malware backdoor attack that do not have any, that are not affected by any known defenses currently in the literature. So this is interesting that it basically shows you at least one approach towards catching some of these attacks that current defenses are ineffective against. So this is promising, and you know, I'm going to try to wrap up and leave a few minutes for questions. So a takeaway from this is that we're trying to sort of sidestep this back and forth cat and mouse game and trying to recognize what makes this cat and mouse game currently so tilted towards the attackers. And it was sort of frustrating to work on the defense side and try to come up with something that was robust. But, you know, so in some sense, we're trying to break out and, as Lorenzo mentioned, you know, trying to find something a little bit more pragmatic, a little bit more sort of directly impactful on real world systems. So several things that we're trying to change. One is we're looking at the threat model and we're saying, you know, instead of looking at a single snapshot, attacking and defending a single snapshot, let's look at sort of a more realistic model where basically companies don't just say, you know, take $1 million or some significant investment, create a ginormous training data set, and then throw one single snapshot out there. That's not how things actually work. They build models, they constantly evolve them with more and more incoming training data. So that is how models actually work, not, you know, here's a binary sort of snapshot, and if you attack it and if you succeed, then I fail and I go home. Nothing as sort of extreme as that. But also from the dimension of like absolute success and failures in the attacks, it turns out that, you know, we can also think of a more general case where the attacks may not succeed immediately, right? So if you look at black box attacks, where the assumption is the attacker is going to come after you with, let's say, 10,000 queries over the network, and the minute they build a sufficiently clear model, they can compromise your model, right? But it may be that realistically speaking, models attacks are much more sort of in some sense partial, right? So maybe they built up partial views of the model that you have using queries. Maybe they sort of iteratively, slowly piece together what comprises the multiple pieces of the attack. That can be a complete model that's not considered right now. And then also, finally, of course, you know, trying to step back and think more broadly about not just preventing the attack from happening in the first place, but broader things like data provenance, for example, and forensics, of saying once in a real setting, attackers do succeed, what can you do after to better secure the system, to detect breaches where they happen, et cetera. So I'm going to try to wrap up there, and hopefully we have a few minutes for questions.
Thank you, Ben. Right, so if you want to ask questions, please ask. Okay, so there is a question in the chat. Did any of the adversarial attacks worked well against face detector, node recognition in black box, and also transferable to physical world?
The Facebook detectors, black box, and also transfer to the physical world. So I'm not quite sure which part of the talk this is. I'm guessing this is related to the physical backdoor aspect of the talk. We didn't look specifically at facial detectors. There's a fair bit of work on that as well. The physical face detectors and also object detectors like, you know, YOLO. And, you know, some of the privacy defense systems are basically looking at how to defeat those detectors. So we did not look at face detectors in particular. Yeah, sorry, I'm not sure if I'm understanding the question, but that's.
Yeah. Hello, Ben. Yeah, I asked the question actually. Like, yeah, I saw like there are many attacks that not work well against the face detectors. What I saw, right. If it is a black box attack, and if we transfer to physical level, physical world. So your research, like, you didn't do that on the detectors, right? Face detectors.
Right. Yeah. So we haven't looked too much at the face and object detectors. Yeah, there's definitely some attacks or defenses, depending on your perspective, that try to break those. But I think in a way that's a difficult space, right? Because there's a lot of different approaches you can make a remote across. Yeah.
Yes, like the most advanced detection systems, they're like very robust against those adversarial attacks. What I saw actually.
Yeah.
Thank you.
Yeah. Sure.
Okay, so next question, Professor Hongmei He.
My question, can you hear me?
Yes, I can.
Okay. The question is about, I think it's slide 12.
Okay.
You have two strategy. I think just two strategy about that.
Sure. No. Is this probably not?
Two strategy. One is you said remove trapdoor related neuron.
Oh yes, the adversarial.
Yeah, I'm thinking about because it's a image based classification, right? So
yes,
the trapdoor is usually located at different places in the image, right? So if you remove this neuron related trapdoor related neuron, might next time is not here. How do you think? How do you make the neural network robust?
So that doesn't. So you're talking about strategy number one, the neuron pruning approach. Yeah, it doesn't really work well. In particular, some of the defenses, if you look at later on when I talked about physical backdoors, the IBM work, neuron activation clustering, that defense is specifically making this assumption that that you have some sort of misbehavior that is localized to specific neurons inside the model, right? We tested that, and it turns out that is particularly effective only against digital triggers and sort of very unusual activations. So in scenarios like in most natural sort of trained inputs, so like in the physical backdoor case, when you have physical triggers that are trained into the attack, they are very well integrated in. So there's not a case of neurons that are so separate that you can basically say, if I remove these neurons, it will be effective. Similarly, in this case, it's very similar because trapdoors, the way that we implemented it, is basically a backdoor. And you can, of course, we actually did the pixel, the digital manipulated backdoors, but you can integrate them well enough with the model in such a way that they are not easily prunable by neuron pruning. And we tried multiple pruning methods. There's at least like 3, I think, different neuron pruning defenses out there. And at least for our tests and all the things that we tested, basically, by the time that you start having impact on the trapdoor, you've damaged benign classification so much that the model is no longer useful.
Okay, thank you very much.
Thanks you for the question.
Okay, so next one is Brian. Brian, do you want to ask him something?
Hi, I've actually put my question in the chat,
right,
saying that the dependability community tends to use the term fault, and in particular malicious fault, for what you call an attack, which immediately makes you think that not all faults are malicious, and there are also accidental faults. And moreover, you often do not have the luxury of knowing which is which until perhaps quite a long way on. But nevertheless, I can imagine that accidental faults will tend to have rather different characteristics from malicious faults. And I was wondering whether your technique has any relevance to both classes of fault. Yes,
that's a great question. That was actually something that, and I'm going to interpret that question in the context of the forensics work. That's actually a question that we struggled with quite a while because we weren't quite sure whether we were able to assume that you knew what type of attack caused a particular misclassification, right? And in a real setting, of course, you have an input and it causes something unexpected. And it's hard to say this is a fault of the model or, oh no, you have an attacker who succeeded. So, but as it turns out, if I can see if I can jump towards this here. Right, okay. So as it turns out, this actually was something that fell out of our work as an accident. Because of the fact that it tends to be this highly separated, this large separation in feature space, if you have poison inputs, we were actually able to then come back and say, this technique of sort of iterative pruning, you can actually use it as a differentiator to distinguish between natural faults and malicious faults, or accidental faults and malicious faults. Because as I think, actually, perhaps Lorenzo asked this related question earlier on, it does happen that when you do have a, gosh, I don't have this in the backup slides, I wish I did, but you know, in our adaptive countermeasure section, when we try to look at this, we try to integrate and we try to find natural sort of accidental faults, but we also try to provide malicious faults where the benign inputs and the poison were so integrated together that the cluster would fail, right? The latter strategy of trying to force poison to mingle together with benign data actually failed. And we were kind of frustrated because we tried lots of different ways, multi-poisons, different combinations of things. They weren't able to really mingle together. But on the other hand, anything accidental turns out that they would have this sort of good integration. And so we were reliably able to detect accidental faults by just using this iterative method and stopping when it failed, right? And by fail, I mean basically you come to a clustering level and you basically see no difference between the two sides of the clusters. And that's when you know that the method, this method has failed. And in every case that we saw, that was because of the fact that it was an accidental fault, not a malicious fault.
Okay, thanks.
Thank you.
Okay, Lorenzo may have a follow-up question or comments.
Yeah, please.
Yeah, I do have. Sorry, I know that I keep everyone a bit longer, but this is really exciting, and it's confirmation bias, but it's really exciting work. So I guess it's kind of related to what you just mentioned here, and I like this approach, the line of direction that you're taking, because it looks to me like there's more like indirect measurement, where in other fields is so common, like astrophysics, for instance, you cannot measure things directly, so you need to observe things from a slightly different angle to understand that something else had happened. Now, my question is, okay, I feel that the way that I'm perceiving this is still, it's still very close to a sort of an in-lab evaluation. Now, imagine that you deploy this. You don't have any luxury to understand the label of what you have, right? Because you have a prediction, but you don't have a label data, so you can actually say, okay, let me just check whether whether I can do this pruning, whether I can do. So the question is, you will have to be doing this on every prediction. Is it feasible? I'm not trying to break it. Sorry, Ben.
Right. No,
so not to break it. Like, I'm trying to understand whether we can actually use this in real life scenarios.
Right. I think. Right. I think I understand what you're getting at, right? So part of the assumption that we're making, and perhaps I should have stated this a little bit more clearly, is that we are assuming that this has a successful attack has already happened, right? And so I think it's a very reasonable question to say, if you don't know whether an attack has for sure happened, how do you use the system? I think it's very challenging, right? So you can't say, let's do this for every input.
Prediction. Yeah, exactly.
And, right. And that for sure will not work. I think the assumption here is that something bad has happened, and perhaps there's a data breach, something else has been triggered, perhaps some other sort of fault line detection system has been triggered, and that something has gone bad, right? Or perhaps you do something preventative, kind of like random sampling of classification outputs, and to see if things are going crazy. Maybe you have a like an orthogonal ensemble model that is in the background double checking, sort of like an inversion inversioning model approach, where you have one external model that's sort of on the front lines and exposed, but you have some backup models that are probably trying to, as accurate as possible as the primary model, but because it's hidden, you can use it to sort of double check and validate the output of the primary. And maybe that would be a mechanism where you can sort of detect something happening badly in real time. But perhaps that's a scenario where the input has already gone through and the attack has already succeeded because you're lagging behind in your validation. But at the very least, then you would know, okay, something strange has happened, and this misclassification result is likely to be a misclassification, and then you do this. But we sort of started with the assumption that something else has triggered the detection, and something bad has already happened. Yeah.
So you basically started with the assumption that you do have this evidence, right? In terms of forensics.
Exactly.
Okay. So
exactly.
Then whether this is realistic or not, how easy it is to get that, it's a separate, it's a separate problem. That's
a little bit harder for sure.
I know. Because if you were able to do that, kind of, you were able to solve that in the first place. But I understand, maybe having some evidence, like at least, to prioritize predictions, like not all of them, but the one that looks really dodgy. And then if you have false positive in that, it doesn't matter, right? Because you're just trying to understand whether an evidence is actually a manifestation of an attack or not, and then you go along.
Exactly.
Very interesting. Very interesting. Very interesting.
Yeah.
Thank you.
Thanks for that great question. That was really good. Yeah. Thank you.
Okay, there is probably one more question in the chat. Did the training IDS based on adversarial attacks effective on rare attacks?
Okay, is this the okay, the training based on adversarial attacks effective on rare attacks? Again, is this with respect to the forensic stuff? I guess. I think, so I think Mohammed asked it again in more detail. What if we train our model based on adversarial attacks to enhance model performance that may be generated by different techniques for the same attack? So yeah, adversarial training. Sure, adversarial training is effective. It can be very expensive. There is usually a price you pay in lower benign classification accuracy. But yeah, it can be very effective. So I'm not sure if you're asking about that specifically. That's certainly a valid approach that is unlikely to be defeated by adaptive attacks. But at the same time, that solution has a heavy price to pay. So there are entire projects and groups, for example, Madhuri's group at MIT, working specifically at how to reduce the cost of adversarial training. How to train it once and then perhaps transfer it to other models. So there's lots of techniques that projects are working at that, trying to reduce the cost of that. But right now, adversarial training is still somewhat limited. And you can only target adversarial training against things that right? And so in a sense, when you ask about the rare attacks, it's very difficult to train against attacks that you don't anticipate. And that's always a challenge for some of these things. That's why forensics in some sense makes a lot of sense, because the assumption is there will be rare attacks that someone is crafting, like a 0-day that no one else has thought of, and boom, it hits your model and it breaks it. So what do you do then? And you're certainly not going to adversarially train against it because you've never seen it before. Thank you for the question. Sounds nice.